Here we have Batman standing on the edge of a building. We're holding onto an 8.6 meter long cable from there to there. And of course what Batman is going to do is he's going to swing down as Batman often does. So he goes from here and he's going to swing down in a circular path. And when he gets to the bottom of the pathway, there is 3,000 newtons of tension in the cable. So what we need to do is try and find out how high he was when he started out. So Batman's going to go from there, and then of course he is going to end up at the bottom here. So we're going to find out how high up he started in order to get this kind of situation to occur. Now there's two things involved in this. There is circular motion and there is energies. It's not just, even though the path is a circular type of path, it's not just circular motion. Since the speed isn't consistent, it works way better to use energies for certain parts of the situation. So if we sort of lay this out, he starts here, he's going to swing down, and let's see if we can use forces to start with. So we got 3,000 newtons of force on the actual cable. Now that force comes from two places. There's two things. There's a force of gravity at the bottom, and there's also Fc, and those two things are pulling on the cable, causing the 3,000 newtons of tension. So let's start with Fg. If we start with Fg, if we just do mass times gravity for Batman, we can calculate that he has a gravitational force of approximately 1,180 newtons. Well, if the tension on the cable is 3,000 newtons, 1,180 of that is coming just to support his weight. So the remaining amount of force must be the centripetal force, which would be 1,820 newtons. So the 1180 and the 1820 come together to make the 3,000 newtons overall. Now that I know his centripetal force of 1820, I can use that to find out how fast he must be going. Now I know his mass is 120. I know the radius would just be the length of the cable, which of course is the 8.6. So I can use that to find the speed at the bottom just by rearranging the expression, and that would be FCR divided by m, and then we'll square root it. And I can find out that he is going approximately 11.4 meters per second at the bottom of the swing. Now since he started at rest, he only had potential energy, and down at the bottom he would only have kinetic energy. So up here we've got potential energy, and down here at the bottom we've got kinetic energy. Now, based on the conservation of energy, those two energies would have to be the same. The change in potential is going to be equal to the change in kinetic. So I can use that idea to solve for the height. So the change in potential is going to be equal to the change in kinetic energy. So the potential energy he started with has to be equal to the kinetic energy he ended up with. Now the nice thing is when I lay it out this way, my masses then cancel off, which makes sense because mass has nothing to do with how fast you fall, and this is a form of falling. So if I rearrange the expression, I can solve for my h value. So h would then just be v squared divided by 2g. So I can use my v value from the bottom, my 11.4, I've got the 2, I've got the g, and I put them into the expression, and I can get a height of 6.6 meters. So that would be the vertical distance he fell in order to swing from the top of the building to his final location.